Hey everybody, welcome back to HPC Tech Shorts, the engineering water cooler here in AWS. Today is part 2 of our discussion about all the new features in ParallelCluster 3.2. In particular, last time we actually covered file systems and all of the stuff that we've done there. In today's discussion, we're hitting Slurm and memory-aware scheduling in Slurm on ParallelCluster 3.2. So there's also a minor change about the way that we're handling. It's a feature we're calling fast failover, but it's essentially when you've got multiple instance types in a particular Slurm partition, how does it handle moving over to the next set of instance types when the capacity of the first set is depleted or not available? So hope you get a lot out of the discussion today. It's Ollie Perks, our senior DA for HPC and ParallelCluster, and with him is Austin Cherian, who's our senior product manager for ParallelCluster and HPC as well. So two most important people in the ParallelCluster universe from my point of view. Anyway, hope you get a lot out of the discussion.
So memory-aware scheduling is an integration between Slurm and AWS to understand how much memory capacity is on each different instance type within our queues, to know where Slurm can actually schedule a job based on the memory requirements of the job.
Right. So this is just because normally Slurm's just worried about cores.
Right, exactly.
That's its primary metric for actually working out if a job's going to fit into a slot on a compute node is, are there enough cores? But
right.
What you're saying,
for lots of people, that's not the right metric to be using. Yeah, if you've got large data sets, you've got large memory consumption. If you stick your job, even if you have enough cores, on the wrong instance type without the memory capacity, it's just going to get killed because it doesn't fit. Yeah, so this is about being explicit upfront and saying, hey, my job needs X number of gigabytes per core, or my job needs X number of gigabytes in total, only schedule it to instance types that have the capacity to run that. Now, the secondary feature of this is where it gets really interesting. And that's when we start talking about co-locating jobs. So that's saying, well, I have an instance type that can support multiple jobs running on it simultaneously. Well, I can protect the number of vCPUs that each of them has and make sure that there's enough capacity there. But we still want to be able to protect the memory capacity so that your two jobs that are running on the same instance aren't actually interfering with each other. So we ring fence the memory requirements of the job and say, hey, you need 10 gigabytes of capacity and 4 vCPUs. You have that and that is yours. And then whatever is left on that instance, we can potentially schedule jobs there, but only if they don't interfere with the memory that we've already allocated to that running job.
So there's a subtlety in here, right, which is that we've put a rule of thumb in here that we're only going to recognize or let Slurm sort of see 95% of the available memory, and that's just simply because operating systems take up some space. Kernels need memory.
Exactly.
And stuff.
Exactly.
Right.
Exactly.
And so that 95% factors, that's our default in ParallelCluster, but we can tweak that, right?
Yes. So essentially, we have also provided a parameter called as schedulable memory, and what that does is that allows you to specify the exact memory for that compute instance. Now, the interesting methodology of how we provide this to the user is, if you look at the diagram over here, we have something called as compute resources. So you could say that we have multiple queues, and I've called that partition 1 and partition 2 over here. So those are 2 queues. And in those queues, you have multiple compute resources. Each compute resource maps to a specific instance type. And so what you can then do is that you can provide the schedulable memory for that particular instance, which reflects on that compute resource to any specific number. In this case, it's 1 terabyte, right? And what this would then allow you to do is that, let's say you have an instance of 1 terabyte of memory, and if you apply the 95% default on that, you end up with wasting hundreds of GBs of memory, basically. And so Specifying it in this manner allows you to actually consume most of it.
So these are a couple of big step changes in parallel clustering 3.2. So is there anything else coming? Is there anything else that we want to cover today?
Sure. There is one interesting feature that we've also brought in, and we can use this graphic to actually explain that. The idea is in the earlier versions of parallel cluster, let's say that you had compute resources. Again, they're denoted by CR in this diagram, compute resources. And you can have multiple compute resources per queue. Each compute resource can define the max count for a instance type. So let's say you take C5 18x large as an instance type that is in compute resource 1. And let's say that instance type has a max count of 100 instances. Now, if you hit a capacity limitation on that compute instance, what used to happen is that parallel cluster used to keep trying as it runs through 100 times, or basically tries to exhaust all of the 100 retries, because there are 100 because the max count is 100 on this compute resource. But with 3.2, what we're putting in is a change in the algorithm which allows it to fail fast to compute resource 2 and sort of block on that particular instance, which is having an insufficient allocation, for example. And so therefore you can actually switch to a different compute instance almost quickly, and basically get the required capacity to run your job and not be blocked or waiting until you exhaust all of the compute instances.
Is there a significant tweak that you just put into the config file, into the YAML, or?
Yeah, so this is a default change, which means that going forward, you don't have to actually tweak the YAML file. It actually is changed by default. However, there is a configuration parameter which is internal to a configuration file, an internal configuration file that you can tweak to get back to the older behavior if you do really want so, essentially.
So we've got two new file systems. We've got OpenZFS and NetApp ONTAP from the FSX folks.
Yeah.
We've got the ability to add lots and lots of FSX file systems now, like 20 per cluster. And if we didn't mention it before, if you've got 20 file systems you need to add to your cluster, we need to talk. And memory-aware scheduling, and then all of this fast failover. So, gentlemen, thanks for coming along today and telling us about all of that. And we'll call it there. So, if anybody out there is watching and there's other ideas you want to see us cover on a future episode of Tech Shorts, or there's more topics you want to see us deep dive into, come and find us on Twitter. Our DMs are open. Until next time, I hope you all have some good computing to be done. Thanks, everyone.